Hey! One to the bright
Right there.
Wait.
Oh,
Yeah, let's get
Yeah, bring it up. Yeah, bring it up.
Bring it up more.
Come on. Come on.
Oh,
Come on.
not bad.
That's it. There you go.
Coma.
Well,
Not
can we get a sense for which is the brightest pixel?
Yeah, just run the cursor around in there.
Oh, there.
Oh.
It's a
Whoa. Not bad at all.
Vicky and my guys. Yes, sir. Yeah, they were.
The previous one.
That's the previous
Previous
one.
one.
Oh,
So we were
we're seeing
560 in the second one.
Well, that looks a lot like, the focus.
Yeah.
It's 20 seconds.
No,
Let's.
Yeah,
Okay.
Still in two.
Put the cursor on the brighter. 24, 600 up 200.
And the rest is history. Dave?
Thanks, Ed. That was pretty exciting, wasn't it? Okay. So why are we specifically meeting here to talk about this today? Well, this is a momentous occasion because, as in 1993, when WFC2 and COSTAR, the other corrective optics device on Hubble, were put in place, this is the mission where they're going to be brought home, hopefully to be properly honored for the role they've played. The second reason is, of course, that we want to be sure that as we go forward and tell the story of how Hubble was saved, that it's fully appreciated what role WFC2 played. I think the almost fairy tale story of the COSTAR is well known, and we want to make sure that the proper relative roles of the two are emphasized as people replay this history over and over. WFC2 took all of those glorious images that you saw between late 1993 and the time when Advanced Camera for Surveys was installed in the last servicing mission in 2002. So whether it's Pillars of Creation, whatever, those were all WFC2 images. COSTAR, you should understand, is extremely important scientifically and has done a wonderful job, but its main purpose was not to support that kind of imagery. Its main purpose was to support the spectrographs, the Goddard high-resolution spectrograph, the faint object spectrograph, and the very high magnification, very small field camera, faint object camera that had been produced by the European Space Agency. So now we had an optical correction for our primary camera with WFC2 and for our other instruments with COSTAR. So I'm going to cover a little bit of the same territory Ed did here with a graphic or two. If I could have my first graphic, please. Okay, this was the first image that came down from Hubble. And it was an embarrassing moment because the press had been invited in to see Hubble first light, and it was supposed to be super spectacular and blow people away. And what you see on the left side is the ground-based image of a simple star field. The star toward the top, the uppermost star, is really a binary star, so it should have been nicely resolved into two separate stars. And on the right is the corresponding Hubble image of that same field. And I think people looked at each other and scratched their heads and said, is that supposed to be how it looks? And I think everyone knew in their hearts this was a bad sign. So next graphic, please. So the problem, as Ed mentioned, is that, and of course, Hubble is not made of lenses. So I'm representing the whole Hubble telescope here with a very simple lens just to illustrate a simple point, that light is coming in, parallel light is coming in from a very distant source in the universe as a beam and intersects the entirety of a lens in this case. And the beams that come in around the periphery of the lens are brought to a focus by the lens at one point. And the beams that come in closer to the center of the lens are focused at a different point. And in a spherical lens, in a spherically aberrated situation, there's no way you can adjust the focus to make all those points come to a sharp focus at the same time, at the same place. And consequently, you get a blurry image, as you see with that upper A. On the other hand, a perfectly produced lens, performing as it's supposed to, brings all of those beams, regardless of where they come through the lens, to the same focal point. So you get a very clear, sharply focused image, and the A has gotten clearer there. Next image, please. Okay, this is a layout of our telescope, and of course we have mirrors, not lenses, and so light comes in from distant astronomical sources through the opening, the aperture of the telescope there at the left, is reflected off our 2.4 meter primary mirror which is the red structure you see there, is focused back onto the secondary mirror, which is about 1/3 of a meter in diameter. And from there, the light is relayed back through a central hole in the primary mirror to the focal plane in the back, where all the scientific instruments and electronic sensors are supposed to get this beautifully focused, crisp field of view of the object being viewed or the star field being viewed. And the problem, as Ed described, was that red mirror was ground down too much glass was taken off. So as in the previous slide, all the rays of light that are coming in at the periphery do not come to a focus at the same position as the rays of light that come in closer to the center of the mirror. It's very classical, very simple spherical aberration. Any amateur astronomer knows to worry about it, and we didn't. Next slide, please. Okay, so that's how the spherical aberration worked, and now pretend the mission is over, the 1993 mission is over, WFP2 is in, COSTAR is in, and I want to give you one astronomical example of how the two have worked together. This is a glorious image taken with WFP2 of a portion of the giant elliptical galaxy M87. It's in the Virgo cluster of galaxies. It's not all that far away from us. And this galaxy is famous for being a strong radio source and for having powerful emissions coming from its very nucleus. And you can see that that jet that's been emitted and all the globules in the jet that you can see illuminated there. And that's a beam, principally electrons, coming out from the center of the galaxy, the nucleus of the galaxy. And forever, astronomers have thought there must be a supermassive black hole as the central engine of what's going on in this galaxy, but they couldn't prove it. And then when we got Hubble up and we wanted to address this issue, we still couldn't prove it because Hubble could not get a clear image. But after the 1993 mission with WFP2, at last we could get a super sharp image. And go to the next chart, please. You can see we've zoomed in now on that nucleus. We see a very bright disk of gas and dust that's rotating, as a matter of fact, at the center. You don't see a black hole because it's black, but you can see the disk of material that's in rotation around it that is compressed and heated and emits light. Okay, so WFP2's beautiful resolution at our disposal for the first time allowed us to really resolve what the center of this nucleus looks like. And now comes the COSTAR part of the story. Next chart, please. And the data you see, the two peaks, you see the lines drawn there on the left, one red and one blue. That's the kind of data that COSTAR allowed the faint object spectrograph to acquire. Those are spectral emission lines. The red line is coming from the part of that disk that's moving away from us in rotation. The blue curve is on the part of the disk that's moving toward us in rotation. And the separation between those two representations of the same emission line tell you how fast the disk is rotating. And what we learned was, in order for that disk not to come flying apart because of essentially the centrifugal forces in the rotation, there had to be a mass, a source of gravity, 3 billion times the mass of our sun, concentrated in a very small volume. So for the first time, WFP2, followed by complementary observations by COSTAR helping faint object spectrograph, demonstrated the existence of a supermassive black hole at the center of a galaxy. So that kind of thing just made us all deliriously happy. It got just one major scientific discovery after another coming online in rapid succession. And the hero of this story is John Trauger. And John, tell us how you did it.
The hero of the story